Morning, sir.
Good morning. Good morning to all. Yesterday, I explained about the throttling process in binary fluid system. Uh, Using graphical solution. This class I am continuing that this process. A few more processes there in binary fluid system. Am I audible?
Yes, sir.
This is
Sir, audible but not clear.
okay. I will raise my voice. I think here some noise is there. Basic noise. Okay, see here the fluid is expanding from 13 bar to 4 bar. Uh, we know the at the inlet the pressure, temperature, and concentration. T, T1, T1, X1. T2 is 4 bar, T2 is unknown, X2 is equal to X1. So to find T2, we have to use this graphical iteration method. The state 1 and state 2 is same, that's H1 is equal to H2 and also X1 is equal to X2. Using trial and error method in this graphical solution, first we have to assume an exit temperature after expansion, and at that particular assumed temperature draw a vertical line till auxiliary and horizontal line from onwards till the reaching to the saturated vapor power. Join the initial saturated liquid and saturated vapor. If this line, which is also called as isodown, is passing through the state, then you may conclude whatever the temperature is there, initial temperature, that is the exit temperature from throttling process. If it is not passing through this point, we have to repeat by adjusting the temperature. By maybe increasing or decreasing the temperature as per the feedback from the earlier iteration. This is a process to find the exit temperature. Now, one more process I am including in this vapor absorption systems. What are the process I am explaining? This is applicable to both cooling applications as well as power generation applications. This process, depleting matter, is also called as distillation. Depleting matter is also called as distillator of the component, and the process is called as distillation. You know the meaning of distillation. This is a refinement of a working fluid. What is the meaning of refinement of a working fluid? If the concentration of the working fluid is increasing through this process, that is called as distillation. Why we have to increase the concentration before supplying to the system, like cooling systems or power generation systems? Cooling system goes to the condenser, throttling, and the evaporator. power generation system means it goes to the turbine. That is the difference. So why we need to increase the concentration? What is the purpose? You know, if X is increasing, that's the concentration of ammonia is increasing. Ammonia is capable of generating low temperature and it works as a refrigerant than water. Got it? So you can expect more amount of cooling effect, and also once you are getting more amount of cooling effect, a COP also can expect a higher COP. So this is the advantage of increasing the concentration of this working fluid before supplying to the cooling system. And what benefit you can get in the power generation system by increasing this concentration through this diffusing matter? That advantage is it is possible to operate the turbine or the plant at lower pressures. No need to maintain very high pressures like 50 bar or 100 bar in case of the power generation system. Once the high pressure range is decreasing, you may design a system at a reasonable price of the material. With the high pressure, let us say 100 bar pressure boiler and these components are designed, the cost of the material and equipment will increase to resist the high pressure. That's why that type of mechanical benefit you can get once you are adding this diffusing matter. But in power generation system, there is no much improvement in the power and efficiency. Performance point of view, there is no much better results you can expect from the diffusing matter. But cooling system, you can get the performance improvement. For power generation, you will get the advantage of low pressure operation. Economic advantage you can get. Coming to the diffusing matter, the process, this first one is the boiler. In this boiler, working fluid is generated, and as usual, as per our explanation, there is a separate region where liquid and vapor is separated, and this weak mixer is going to mix at the inlet of the absorber. That we also solved, discussed in the earlier class. That is adiabatic mixing and diabatic mixing. Also separation process. And throttling is not shown here because this process is focused on this diffusing matter component only. After this separator, let us say the state 6, it enters into the diffusing matter instead of straight away entering into the condenser or turbine. In the diffusing matter, what is happening? I think these components you are already aware, boiler and separator. In boiler, what is happening? The liquid is converted into the liquid vapor mixture by absorbing heat, maybe from outside, renewable or non-renewable energy. The liquid is converted into the liquid plus vapor. The liquid has been separated. It is also called as weak solution because of lower concentration, and that this vapor is alone we are using as a main working fluid in the system. So this additional component diffusing matter, what it is doing, it is providing some cooling effect. So some heat has been rejected from this working fluid. This is a mixture of, let us say 6 is a mixture of ammonia and water. Of course, this is the yellow color is pure vapor. The yellow color is pure vapor. At the inlet of the diffusing matter, the status is saturated vapor. Now you are rejecting heat means saturated vapor becomes cool. The temperature of this working fluid is decreasing. Now I want to ask you one question. This is the vapor of ammonia vapor as well as water vapor has been mixed together. You are providing a cooling surface. Which one condenses first? Water will condense first or ammonia will condense first?
So water.
Yeah, water will condense first. Yes, you are correct. May I know the reason?
So because ammonia is very low.
Yes, correct. In the cooling side, You are decreasing the
Yes, sir. So
temperature. During the
compared to
journey,
water.
yes, you are correct. First, boiling point of water will come, and then later subsequently, if you are still you are cooling means boiling point of ammonia will come. The boiling point of H2O is more than the boiling point of NH3. That's why water first starts condensation, not ammonia. Ammonia also maybe small traces may condense, but majority of the vapor is the water vapor only. Water vapor is condensing, then automatically what is your resultant fluid at 9? The condensate you may see as a blue color in the deplimeter. The yellow color again, what you are expecting compared to the 6? Are you expecting increase in the concentration or not? Because you are removing the water. So obviously the concentration will increase. It's a more ammonia based vapor. Are you getting this point? 679. 679 is a process of different matter where 8 is coming out as a condensate. But again it is recycling in the boiler. Okay. So now you got the point. What is the purpose of this liquid matter? How it is working? So by providing this heat, heat may be rejected to the surroundings, or maybe internally also you can recover internal heat recovery instead of wasting this heat to the surroundings. That heat also can be recovered like internal waste heat recovery. That thing is different. That is thing. Now our focus is how this liquid matter is working. So by rejecting heat, the concentration is increasing from 6 to 9. So this high concentrated vapor you can condense, throttle and send to the evaporator, where you can generate more amount of cooling effect compared to without liquid matter. Okay, now in analysis point of view, or some numerical calculation solution successes point of view, we have to define the performance of this liquid matter. Okay, to find this performance of liquid matter, we have to define this performance parameter based on the target. Okay, you know, effectiveness of heat exchanger. How effectiveness of heat exchanger is defined? That's maximum possible temperature difference. T max, T minimum. You know, accordingly you define the efficiency of the pin or effectiveness of heat exchanger like this. Okay. Now similarly here also, what is the maximum possible distillation condition? You know, what is the maximum possible distillation condition? Critically you may assume what the maximum extent we can do this distillation. I am saying practically it may not be possible. Critically means you can imagine, there is no limit for imagination. They ask you, what is the limit for this distillation? If the concentration is increasing, even increasing, what is the maximum limit of this concentration? At 9, state 9. Hello? What is the maximum limit of concentration after the depleting matter at state 9 before supplying the plant?
Ammonia.
Yes, ammonia concept. What
X equals to 1.
Very good, very good. X is equal to 1. Excellent. So 100% is the maximum limit. So if you are able to remove all the vapor, that's water vapor or H2O from the mixer, the balance is pure ammonia. If you are sending pure ammonia as a replacement, that's excellent actually speaking. That is the target. That's the maximum limit. Okay, for cooling point of view I am saying. So, but actual distillation is less than that point. Maybe instead of reaching 100%, you may reach 95%. From 80% to 95%, for example. At the inlet, this is 80%. You reach the 95% with the goal of 100%. So with this difference, you may find some performance parameter like 95 minus 80 divided by 100 minus 80. Got it? 100 minus 80. So the actual distillation process by maximum extent of distillation. Actual distillation and maximum extent of distillation, that is of the target of 100%. You may define this the performance condition like COP of this. We can't say COP. This is a performance condition. I will define some name. I will give you. That is for the diffling matter. We now see on the chart, that's enthalpy concentration chart. This I am showing for diffling matter process, and the separation also included to understand the connection between the separation and the diffling matter. Because in the earlier drawing, the schematic sketch, the separation process we are seeing the 4, the working fluid at 4 has been separated to 5 and 6, where 5 is a liquid. The 4 has been separated to 5 and the 6. 1 minute please. It's maybe include this here itself. Sorry. Now it's fine, I think so. The 4 has been separated to, what is the 4? Okay, sorry. Four has been separated to 5 and 6. You are clear about the separation process. We also had the discussion of this 4 to 5 and 6, and by applying this Lever rule, we also framed them formulations. Okay, from 6 onwards, 6, 7. What is 6 and 7? 6 to 7, there is a heat rejection. Heat rejection means there is enthalpy is decreasing. The concentration is same. See here, from 6 to 7 before separation, 6 to 7 before separation of this condensate, just heat rejection. For 6 to 7, I am showing as a vertical, there is a downward line since enthalpy is decreasing. So 7 has been separated. 7 has been separated to liquid 8 and vapor 9. This is a liquid 8 and vapor is 9. Otherwise, I can also show 6 to 8 and 6 to 9, but thermodynamic point of view, for easy understanding, the heat rejection process has been shown separately, and the separation process has been shown separately. Same like diabatic mixing. The diabatic mixing I explained like adiabatic mixing plus heat transfer. It may be positive or negative. So similarly here also, the heat rejection followed by separation has been shown to understand the process of diffling matter. Now you can clearly see how extent this concentration is increasing from 6 to 9. Just 6 is the inlet of the diffling matter, and 9 is the outlet of the diffling matter, and concentration is increasing from 6 to 9. But it's not exactly 100% because the state well I defined hypothetically, if the process is going to 100% of this concentration. So this 7 is the actual, so 9 is the actual position after the diffling matter. If you are assuming 12 is the ideal position, 12 is the ideal position. Yes. And you are extending the vertical line, but you are continuing this heat rejection. You didn't stop at 0.7. The more heat rejection you are doing, still getting 100% purification. So where you are stopping at state 10, you stop. Why you stop here? Because you got 100% vapor. Got 100% vapor. That's why you stopped at state 10. And at state 10, you remove this H2O, that's a liquid part, and this the vapor part consists of pure NH3. This is a limit. So now You may define this process. This 6 9 is the actual process, and 612 is the ideal process of this concentration I am saying. And coming to this heat transfer or heat rejection, 6 7 is the actual heat rejection, 6 10 is the maximum extent of heat rejection to get 100% of this NH3. That's it. Depletion process, maximum depletion process to define effectiveness of the process. Yes, now I am saying this term, effectiveness of depleting matter. The effectiveness of depleting matter you may define X in and X exit and X. This is 100%. At the maximum limit, it is 100%. So as I gave the example of 80 to 95%, 80% to 95% is actual, and 80% to 100% is maximum. Then effectiveness of this depleting matter you may calculate by 95 minus 80 by 100 by 80. Is it correct? So you may calculate this effectiveness of the depleting matter according to the given conditions. So this definition is useful in the numerical problems and also to define the what extent the actual depleting matter process is going on. And also you can analyze the process, depleting matter process, because the depleting matter process gives times the favorable conditions and unfavorable conditions, because we are rejecting the heat to the surroundings. We are losing some energy. At the same time, of course, we are getting some benefit for cooling system, but power generation system, there is a loss in power because some of the working fluid we are removing. See here, a condensate is coming out without entering into the plant, maybe cooling plant or power plant. Some of the working fluid is returned back to the boiler without you doing any work, any task, cooling task or power task. So that is the loss. Even though there is some benefit for increasing the concentration, that's why there is maybe some optimized conditions. We can analyze this depleting matter, and we may recommend some optimum distillation conditions to get the better performance based on the objective function. The objective function may be maximizing the cooling effect or maximizing the power or maximizing the COP. That depends upon the case. Okay, now the heat transfer in the heat exchanger, especially the boiler. This drawing is prepared for a complete boiling process. A complete boiling process, not for partial boiling process. This is the temperature heat transfer diagram. The hot fluid temperature is decreasing. Let us say it may be the hot gas or it may be oil in case of solar system. That hot fluid temperature is keep on decreasing. And what about the working fluid? In boiler, in case of heat recovery vapor generator, it can be divided into 3 sections. Actually, this drawing is drawn with scale. That's why the actual shape you can see here. The 3 sections consist of economizer, the second is evaporator, and third is the superheater. Okay, SH means superheater. And now 1 2 is a sensible heat transfer, I can say, because there is no phase change in 1 2. 2 to 3 is latent heat, but the latent heat of H2O and latent heat of NH both are applicable here. That's why the temperature is not constant because of the binary fluid system nature. The starting temperature for the phase change is bubble point temperature, and the ending of the phase change is dew point temperature. You can also see same like sensible heat transfer, a latent heat transfer also with a variable temperature, not constant temperature like single fluid system. Of course, superheater also sensible heat transfer where the temperature of the vapor is rising, but the slope is different. See, the slope of economizer, evaporator and superheater is different. This depends upon the thermal properties that you can see, specific heat of or latent heat of this single fluid system or multi fluid system, and according to the region like liquid region, liquid vapor region, and the vapor region. So this is the heat exchanger for a typical boiler, which is working on heat recovery systems. Okay, now systems. I will give a brief outlines of the systems, both vapor absorption refrigeration system, and also vapor absorption power system, which is also called as power generation system. Because these systems we are going to use as a subsystems in the power generation plant. Okay, just 1 minute. Are you seeing a screen here?
Yes.
Yes, sir.
Okay, I'm now I explain the process separately. Now I am combining all this process to get this refrigeration cooling effect. Okay, where I have to start? I will start from the boiler. Okay, that's my easy. The boiling process. I'm showing one is this is internal fluid, that's for working fluid we are saying, and heat has been transferred to the external fluid, maybe solar system or any other system. So this working fluid has been generated in the boiler. At the exit of boiler, the status is liquidous vapor. So this liquidous vapor has been entered into a separator. In the separator, what it is doing? The liquid has been separated and vapor has been separated. So this vapor again it enters into another heat exchanger. That's we can also call as diffling matter. The heat has been rejected to the surroundings or maybe internal. So here some condensate you can see here. That condensate again it is going back to the boiler. Again going back to the boiler, and this pure vapor, I can say it's enriched vapor enters into the system. Now our heading is refrigeration system. How we have to use this working fluid? This working fluid we have to use for the cooling purpose. What are the basic components of this cooling system? This may be vapor absorption refrigeration system or vapor compression refrigeration system. Their common components are condenser. After condenser, throttling. Next, evaporator. So these three components are common in both the vapor absorption system as well as vapor compression system. The difference is compressor. Here we are calling this system, the boiler and pumping system, as a thermal compressor, because except now we are not using any high grid energy. Whereas in mechanical compressor, we have to supply more amount of electricity, it's high grid energy, to operate the compressor. That is the basic difference between the binary fluid system and single fluid system for the fluid purpose. So now it has to, this is completely vapor, The vapor at the high pressure, it has to condense. How to condense? Again, it is a heat exchanger. I am sending this condenser. Okay, this is heat exchanger coil has been used here. The vapor has been condensed. That condenser is supplied to the throttling device. Of course, here we can also use some subcooler. I'm explaining the basic components of this vapor absorption system. So step by step, you may improve the internal heat recoveries and some subcooled heat exchanger for subcooler, those things to improve the COP of the system. So coming to the basic components, after this condenser, this is a condenser. After throttling, where it has to go? It has to go evaporator. Evaporator is also a heat exchanger. Evaporator is also a heat exchanger. In evaporation, what is happening? For example, I am sending a fluid here, a liquid. Then you can generate the chilled water. That means you are absorbing the heat from the surroundings. That's why it is called as evaporator. Then the liquid becomes a vapor. When the liquid becomes a vapor, that vapor you have to condense. That vapor we have to condense in the condenser. But see, as I explained in the earlier class, we can't condense this vapor straight away at our sink operating conditions. Why? Because this concentration is high. You are using this depleting matter. This is depleting matter. The separator and depleting matter is increasing the concentration of this working fluid. It's more than 90%. So to condense this vapor, of course this is condensed, again it is coming to the vapor, it's expanding from high pressure to low pressure. So we need to maintain very low temperature, means maybe 5 degrees or 10 degrees. What I'm saying? Yeah, straight away, what we have to do now? What we have to do? We have to dilute. We have to dilute this system before supplying to the condenser. How to dilute? That process is called as absorption process. So this liquid can also called as weak mixer. But this is a high pressure, but this is a low pressure. That's why you need to keep the throttling device. This throttling is not to generate the low temperature. This throttling function is different. This throttling function is different. This throttling is creating low temperature. Because we are creating low temperature because the concentration is high. But here you can't create the low temperature. Because this is a weak mixer. This is not the rich mixture. So just its expansion purpose only this rod has been used. So after that, I am skipping some of the internal heat recovery here to explain the basic simple vapor absorption physical system. Then the liquid is absorbed and mixed with the vapor, or this vapor is absorbed into the liquid. Then this mixture easily we can condense into the saturated liquid condition. Without this process, absorption process or mixing process, we can't do the condensation. Okay, now we can add the condenser here. To reject the heat, you can keep either air-cooled condenser or water-cooled condenser, and you reject the heat, so you can get the condensate. So since it is absorbing the vapor like magnet into the liquid, it is called as absorber. This component is called as absorber. Now after this condensation, actually this is also condenser same like this one, but here the difference is they are only condensation, but they are mixing and followed by condensation. That's why especially we are calling this as absorber. So this can be pumped to the boiler, so you can keep some pump and that liquid is entering into the boiler. So the pumped solution, the temperature of this pumped solution can be increased by transferring heat from this fluid. So you can add some internal heat recovery between this weak solution. Weak solution is relatively high temperature, and this after pumping the temperature is 40-45 degrees centigrade. So there is a chance to recover the heat, same like the steam power plant. So the preheating of this liquid saves the boiler load, and you can get the benefit of improving the CO2. Okay, now this is vapor absorption refrigeration system. What I explained here, the components of boiler, separator, igniter, condenser, throttling, evaporator, absorber, pump. And the concentration is relatively, this weak solution concentration is low concentration, okay, maybe 0.3. But this concentration which is entering in the absorber and the pump and boiler, this concentration is higher than this weak solution. That's why this is called as strong solution. Here I can write here. I write here. Strong solution. Now you can see the three branches, mainly three branches when collecting this liquid matter. There is a vapor working fluid line. This is the working fluid line, and weak solution line, strong solution. Okay, this is the working fluid, it's a vapor, and this weak solution, strong solution. Okay, fine. So, and then whatever we have the discussion, that is the solutions of the heat exchanger, separation, condenser, liquid matter, throttling, evaporation, pumping, absorber can be combined together to get the overall outcome of this vapor absorption system, and how much heat energy has been supplied, both low grade energy as well as high grade energy, and how much heat we are absorbing here. These conditions will give us COP effect, coefficient of performance. That's the outcome is refrigeration effect, and input is both this high grade energy and this low grade energy. And mainly the driving force is okay, pump, it is pump, and the mixing, that's the mixing process as well as the separation process also. Thermally, it is also creating some drive. It's creating some drive. That's why some very low capacity vapor absorption system without pump also is possible. That's a complex vapor absorption system also at the laboratory level we can see. Okay, that's a very small capacity. Are you clear about this vapor absorption refrigerant system? Do you have any questions? This we are going to keep as a subsystem in the college education. And advantages and disadvantages of this vapor absorption refrigerant system is COP is low. COP is low. And advantages means I can say the binary fluid system. Advantage of binary fluid system, the heat addition, that's the temperature is variable, heat addition, and also temperature of working fluid is variable in condenser as well as observed. It is a close match between the external fluid and working fluid. That's advantage. COP is low, and any else? Bulky. Disadvantages is bulky. Bulky means the size of this vapor absorption diffusion system is too high compared to vapor compression refrigerant system. Vapor compression, see here is split AC, the window seat, the size of the component, mechanical compressor is small size. But it has so many components. See here, vapor absorption refrigerant system. Additionally, you are using the boiler, separator, deflector, absorber, pump, which are not the part of vapor compression refrigerant system. Vapor compression refrigerant system is simple components basically for the mechanical compressor, condenser, throttling, and evaporator. That's all. But in place of mechanical compressor, how many components are adding? Absorber, pump, boiler, separator, deflector, throttling, the mixing process. I didn't use few more like a high temperature regenerator, low temperature regenerator. I didn't show here. So many extra components has been added. That's why it's costly. The size also is more unsuitable for the medium and high capacity systems. Like, for example, if I want to make a 1 ton of vapor absorption system, it's difficult. The small size vapor absorption system, it's as per the current market availability. I am saying this statement. Future you can find even small size vapor absorption system also. Maybe as per the current market condition, I am saying. Mostly, as per my knowledge, the minimum capacity of this vapor absorption is 5 tons of liquid. 5 tons, 10 tons, that much size we can get. But small size, like fractional tons of liquid system, so far, because of this issue, I think so, the bulky system, that much small size capacity. And this is not suitable for the domestic applications. Not for domestic applications. Why not for domestic applications? This working fluid is NH3 plus H2. You know the problems, the health problems of this NH3 plus small increase, the respiratory system, the issues will come. It's a toxic in nature also. But environmentally it's fine. NH3 won't harms the atmosphere because there is no ozone depletion effect and there is no global warming of this NH3. That's fine. But human body point of view, respiratory point of view, NH3 is issue. And also the properties point of view, the mechanical, material point of view, also this issue is there. NH3 is more corrosive. We can't use any copper or its alloys. We have to use iron, steel, etc. other than copper. That is also one of the issues. See, most of the material used in vapor compression system is copper only. You can see a lot of copper tubes, etc. At some extent, maybe aluminum heat exchangers. But here, the copper we can't use at all. That's NH3. Aluminum is okay, but still it's a small rust. We can see the prolonged time with aluminum. As per my laboratory experience, I am saying. That's why steel or iron is better for NH3 operation. So these are the issues, some of the challenges and issues for this vapor absorption system. In next class, I will explain the same vapor absorption system for power generation, because it is also called as the Kelvin system, and followed by some solutions, classroom solutions, and I will teach both using the analytical approach as well as graphical approach. Do you have any questions? Because I'm coming out from the screen. And this once I'm coming out from the screen, I can't get back. It's one direction.
Sir, what is the range of COP?
Okay, definition of COP. Right?
No, sir. What is the range of COP?
Okay,
The
very
VARS system.
Yes, I told COP is low. The COP, a typical single effect. This is called a single effect system. COP is approximately is equal to 0.3. But triple effect, it's 0.7, 0.9. There is one more vapor absorption refrigerant system is there, lithium bromide and H2O, LiBr plus H2O. This is suitable for the domestic applications. But this is not suitable for below 0 degrees centigrade. This is not suitable for below 0 degrees centigrade because here, but the refrigerant is H2O. We can't condense this H2O below 0 degrees centigrade. This ice formation blocking of the pipe synthetic space. But in NH3H2O, we can operate this system even below 0 degrees centigrade also without any blocking effect or the freezing effect. And they are useful mostly for industrial applications like cold storage. In Gurgaon, I visited one solar cooling system, that's a solar energy center long back. They have triple effect, lithium bromide, H2O, vapor absorption refrigerant system. The COP of triple effect this vapor absorption is 1.27. 1.27. Single effect means less than 1 only. That's why generally I am saying the COP of vapor absorption refrigerant system is less than 1. But vapor compression refrigerant system 3.5, which is too high compared to the vapor absorption refrigerant system. They are rich. They are using high grade energy. But this vapor absorption refrigerant system has the merit of you can use the waste heat, renewable energy. Waste heat means there is no any much investment except the equipment. That's why this vapor absorption system has a great potential, especially once we are designing for the poly generation systems and also low grade energy, solar energy systems. Are you clear about the COP value?
Yes, sir.
Any else? Mishra?
Yes, sir.
Do you have questions?
No, sir.
Okay, may I skip the... Okay? I am changing the screen, okay?
Okay, sir.
Right. So, 1 minute. Today I will add this data book. This data book consists of, this is also a part of poly generation system. Here nomenclature of refrigerants, and even starting BTech refrigeration system also, students also they can use this data book. Properties, actual properties. That is our point of view, the subject point of view. This is enthalpy. Okay, this is enthalpy concentration chart up to 20 bar I prepared, and I also include for vapor power generation system up to 100 bar. Also, I am going to include one more chart. This chart is suitable for solving the cooling system and refrigeration system. You may see 3 sets of curves here: the liquid, auxiliary, vapor. The liquid is These are the saturated liquid. You can also see the temperature curves. Which are then showed in the right-hand sketch. These are saturated liquid as usual. There is a temperature. Yes, 220, 200, 180. These are all the dotted lines. Blue dotted lines shows the temperature. These are the temperature curves. So, for example, there is one point is that at this point, my cursor, I can read pressure, concentration, temperature. Three properties we can read. PTX, three pressures we can read from the graph, which is a liquid condition, which may be saturated liquid or subcooled liquid. Okay, I will explain this graph while solving the problems for the process as well as the plant. This illustration is different because for desalination I am going to explain, especially for simplification desalination I am going to explain the cyclometry. You are aware about the cyclometry, but here what I am adding here is cyclometric chart you know very well. But cyclometric properties also I prepared, which is not available in the literature or textbooks. So we have freedom to use these equations, charts, cyclometric chart, or like steam tables. You know how to use the steam tables to solve the steam power plant. Similarly, air conditioning or desalination, air conditioning related desalination system. The properties, you can pick the properties from these tables, same like steam tables. But this cyclometric has more flexibility in properties like tribal temperature, relative humidity, and dew point temperature, vector temperature, specific volume, degree of saturation, specific humidity, saturated specific humidity, and specific enthalpy, specific entropy, specific exergy. So you can solve both the energy as well as exergy. Because cyclometric chart won't give the entropy, I think so. It won't include the exergy values. So that I included this entropy as well as exergy so that you can extend second law analysis for this type of polygeneration system. Okay. The binary fluid tables I have to include here because I made separate file for binary fluid system, that's it, tables. I will add that one also.
So we don't.
Some of the chapters here, IIT Kharagpur chapters, you can download and prepare these lessons. Some journal papers of this polygeneration introduction. Okay, fine. Yes, somebody asked me.
So we don't get the attached document in polygeneration data book, sir.
Standard.
So we don't get the attached document in polygeneration data book, sir.
Books, you are asking books?
Yes, sir. The polygeneration data book which you have shared, so we don't have get the, so we don't get the attachment there, sir.
Yes, I know. Today I am going to attach. Yes.
Okay, sir.
I didn't attach actually. I am going to attach.
Okay, sir. No issue.
Akshay Sangra is absent. Avnish.
Fine, sir.
Avnish.
Present, sir.
Manoj.
Present, sir.
Deepak.
Yes, sir.
Jahid. Why Jahid is not coming? Sia.
Yes, sir.
Why Jahid is not coming?
So I'll ask him, sir, today, sir.
Yeah. Maupriya Das. Maupriya Das. Absent. Sukesh. Sukesh Ghosh. Swapnil.
Present, sir.
Vaibhav. Yuvraj.
Sir, Vaibhav was there, sir.
Why is not called? Okay, Yuvraj.
Yes, sir.
Sir.
Yes.
Okay, are you seeing the screen? The marks and I am showing.
Yes, sir.
Yes, sir.
Yes.
Okay, I think if any deviation is there without reading, just you can note me and change. It's fine. 1, 2, 4 students absent. No, 4 students absent. Okay, fine. Tomorrow.
Thank you, sir.
Bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.